We were adding, subtracting, and multiplying matrices. We've identified a few important matrices like the zero matrix and the identity matrix. So now let's talk about matrix multiplication and multiplying a matrix by itself. So matrix powers. You're taking a matrix to a power. Essentially what you want to be able to do is you want to be able to just multiply a matrix by itself. And that's how matrix multiplication is going to work. Now we just have to be careful and remember that matrix is not commutative. And because it's not commutative, for raising a matrix to a power is not a big deal because it's the same matrix. So whether you switch that around or not switch it around, it doesn't matter. But there are going to be times later on where the commutativity might make a difference. But for now, let's talk about matrix powers, multiplying matrices. So if we are going to raise a matrix to a power, remember that the column for the first matrix has to be the same as the rows for the second matrix. And if it's going to be the same matrix that we're multiplying, they basically have to be square matrices. So we can only take matrix powers, exponents for square matrices. I'm not like that, am I?
No.
It's like falling off.
Probably don't know we have class.
All right, let's define a few things. A matrix to a first power is going to be itself. A matrix to the second power is going to be A multiplied with A. The one that's not so obvious is the matrix to the zeroth power is the identity matrix. Now that's you know that anything to the zeroth power is 1. We know that for real numbers, but that also happens to work for matrices. And for now, let's just say that that's true. And then we also have the basic power properties for real numbers that also work for matrices. And that if you have 2 matrices raised to a power and you're multiplying them, it's the same as adding the powers. What? Wait, did that make sense? It's this one. If you have a matrix to a power times a matrix to a different power, it's the same thing as adding to a power. And this could be laid out like this, almost the same proof, same way to prove it with real numbers as well. You know, we just list down R matrices and S matrices, and you put them together, and there's R plus S of them that you're adding. Okay, well, we could do an example, but I think it's better to take a look at some examples of interesting matrices and taking them to a power. And with these interesting matrices, taking them to a power kind of leads to a pattern. So let's take a look at one of those examples. Let's take a look at 1, 1, 1, 1 as a matrix, and then let's do some basic matrix multiplication and see if we can come up with a pattern for that. So a squared is going to be 1, 1, 1, 1 times 1, 1, 1, 1 And if you remember how to multiply, we just kind of learned it yesterday. We're doing row times column, or the dot product, and then and then that's going to be the first row and first column entry of your resulting matrix. So 1 times 1 plus 1 times 1 is 2, and then we're going to go on and do the same thing for the others, right? So 1, 1 dotted with 1, 1, that's also going to be a 2, and we're going to get a bunch of 1, 1s times 1, 1s. So A squared is going to be 2, 2, 2, 2, a matrix full of 2s. So A cubed is A times A times A, and then we didn't talk about the associative property of matrices, but matrices are associative, and so we can say this is the same thing as A squared times A, or whatever. So A squared is 2, 2, 2, 2. Let's multiply that with A, which is 1, 1, 1, 1. And does it? 4, 4, 4, 4. Okay. So looks like it might double every time. Let's do it one more time just to make sure that we can find the pattern. A to the fourth is A cubed times A, since we have A cubed. So that's 4, 4, 4, 4 times 1, 1, 1, 1. And that is going to be what? 8, 8, 8, 8. So, do we see a pattern? Two to the n minus 1. So let's check a pattern here. Let's say A to the k is equal to 2 to the k minus 1, 2 to the k minus 1, 2. Can I write this a little bit easier or neater? Factor out the scalar, right? How do we factor out the scalar? You just take it out. 2 to the k minus 1. And what do we have left? 1, 1, 1, 1, which is the A matrix, right? So I think this is a good segue to talk about a formal proof of something like this. Seeing a pattern and then establishing a formula for the pattern isn't necessarily a proof. So for those people that are going to go do more math in the future, you have to familiarize yourself with different ways of proving things. And one way to prove this, or a way to prove this particular type of problem when you see a pattern as you go through the counting numbers, natural numbers, is called a proof by induction. So I think maybe it's a good time to introduce induction. So let's actually prove this. So we're going to do B and C in another page. So let me just cross this out for right now. And let's talk about prove A to the k is equal to 2 to the k minus 1 A. By induction. Oh, so this has to be true for k is equal to you can't start with 0, so k is equal to 1, 2, 3, So counting numbers. So these are called the natural numbers, right? And sometimes they're called the counting numbers. You know why they're called counting numbers? There's another, because what? You start with 1. And when you first learn how to count, they teach you to count from 1, right? Remember when you were like 8 months old and somebody was saying 1, 2, right? So as parents, if you're a computer scientist, I think computer science parents should teach their kids how to count from 0. 0, 1, 2. Anyways, the set of numbers 0, 1, 2, 3 are called, what are they called? They're called whole numbers. Okay, so natural numbers start with 1 and all the integers. Whole numbers start with 0, 1, 2, 3. And then integers are positive, negative whole numbers. Okay? Zero is not positive or negative, so 0 doesn't count. Okay. Anyways, we're going to try to prove this by induction. So proof by induction, there's 3 steps. The first step is the base case. Step 1 is the base case, and the base case is going to be the first one. So a to the first power is equal to 2 to the 1 minus 1 times a. And this is true, obviously, right? So these things are, the base cases for these things are almost trivial. They're trivial in the sense that they're always going to be obvious. But we got 1, 1, 1, 1 is equal to, what's 2 to the 0 power? That's 1, so it doesn't change your matrix A, which is 1, 1, 1, 1. So that checks out.
A little off topic, but is that a proven thing? Integer to the 0 equals 1.
Well, it's not necessarily proven. We kind of used it as something that was defined.
But I mean, in math, is that a proven thing? Or
Yeah.
did they just define that?
No, it's proven somehow, somewhere. So that's step 1. So step 2 actually is not a, it's a, how should we say it? Step 2 is not something that you do, it's an assumption. So step 1 is prove base case. Step 2 is assume true for k. So we're going to say assume that a to the k is equal to 2 to the k minus 1 times a. So we'll assume that. And then step 3 is your final step. And if this proof is at all difficult, this is where you would find the difficulty. This is prove for k plus 1. So you're going to assume that it's true for everything less than k up to k, and then you're going to assume that it's going to be true for the next step. And that's how the proof for induction goes. All right, so let's consider a to the k plus 1. So what we're going to do is we're going to use definitions and our assumption to see what this is going to equal to. So a to the k plus 1, that's equal to a to the k times a. And a to the k, according to your assumption, and this is where you use the assumption right here in this equality, is equal to 2 to the k minus 1 times a times a.
That's what we display our assumption to find that equals.
Yes. Yeah. I mean, it might be good to note assumption that this is where you actually use the assumption. And somewhere in step 3, you're actually going to use what you assumed in step 2 for this to work out. And then from here, you can just kind of do the work. We got 2 to the k minus 1. And then a times a, we did this as background work, but you can redo it again. I'm not going to redo it again. I'll just say a times a is a squared, which we did, and that's 2, 2, 2, 2. And then you can finish this off by multiplying this scalar through, and then that would be 2 to the k, 2 to the k, and then you can factor it out again. Or you can just, probably didn't need to do this step. So if you take the string of equalities where you started from and where you ended, that's the end of your proof. So you've proven that a to the k plus 1 is equal to 2 to the k times a, which is the next step, which is proven for k plus 1. So you can say you're done here. You can have a little something there to say that you're done with a proof. Or yeah, you can say QED. So, or you can use this. Oh, if you get to higher math and you start proving all kinds of stuff, you'll find your little symbol for the end of the proof. QED. What's QED stand for? What? Era. That which was to be proven. So that's the end of the proof. So that's the proof for the first one in finding the pattern and proving the pattern. All right? Wow, that's a good test question. Proof by induction. So there's a couple more here. I won't prove them, but let's take a look at some patterns for them. For B, let's start off by finding b squared. 0, negative 1, 1, 0 times 0, negative 1, 1, 0. And do that row, first column goes in the first row column. So 0 times 0 plus negative 1 and 1. 0 times negative 1 times 0. Now the bottom row, 0 times 0 times 1, and then 1 times negative 1, 0 and 0, so that's negative 1. Is that right? Okay. So this is b squared. Let's take a look at b cubed. So I'll take b squared and multiply it times b. So that's -1, 0, 0, -1. And b is equal to 0, -1, 1, 0. What? Is that right? Okay. Okay, so first row, first column, -1, 0, 0, 1, so that's 0. First row, second column, -1 times -1 is +1. 0 times 0 is 0. Second row, first column, 0, 0, -1 times +1, that's -1. And 0 times -1, -1 times 0. So that's b cubed. Let's go to the fourth power, b to the fourth. That would take b cubed times b. 0, 1, -1, 0 times b, 0, -1, 1, 0. All right, first row, first column, 0 and 1. First row, second column, 0 and 0. Second row, first column, 0 and 0, and then 1. Okay, and let's go one more. B to the fifth is b to the fourth times b. B to the fourth is, what can you say about b to the fourth? That's identity matrix, right? So if we multiply this by b, it'll just be b. Okay, so we eventually got to b, and then if we have b to the sixth, then we're kind of going to recycle this, and it'll kind of look like b squared or something like that. So I think at this point we kind of established some sort of pattern here. Does this, I don't know, does this remind you of anything? It look like they're rotating. The top two is being multiplied by -1. Sine, cosine, and how the derivatives work for sine and cosine. It's getting warmer. Right? The derivative of sine is cosine. Derivative of cosine is negative sine. Derivative. So there's something going on there. Anything else?
Like a -1 being powered number of times.
-1 being powered number of times. That's kind of close. Kind of close. Yeah, there's some -1 in there, and there's some stuff being powered a number of times.
-1 to the k minus 1.
No.
To the pi.
To the pi? No. Okay, stop. Those are good ideas. So let's take a look at B again. B to the 0, which is the identity matrix. No. B squared, b cubed, b to the fourth. What's b to the fourth? This is the identity matrix again. And then it recycles. It cycles back. So there's 4 things. It takes 4 powers to get back to the original. B. Yeah, so imaginary numbers is what I was looking for. Yeah. So compare with I to the 0, which is 1, I to the first power, which is I to the second power, which is negative 1, I to the third power, which is negative I to the fourth power, which is 1, I to the fifth power, which is I. And how it's kind of looking at the same pattern. So it does have something to do with sines and cosines. And hey, look, there's a sine and cosine here. Hey, what if theta was say equal to pi over 2? What if theta was equal to pi over 2? What's cosine of theta? Cosine of pi over 2? 0. What's sine of pi over 2? 1 with a negative. Sine of pi over 2 is 1. Cosine. So it does have something to do with sines and cosines. It does have something to do with imaginary numbers. Pretty cool, huh? That's all I need to say about that. I think you guys can... No. You can. This is
Pi, right?
what?
Pi to the 1 is pi, right? Forgetting about imaginary numbers. Because it looks like IW.
No, I'm sorry. This is just I. I got a little squiggly. Anyways, if you look at C, if you look at the matrix C, and let theta equal to 0. Let theta equal to pi over 2, then let theta equal to pi, and then 3 pi over 2, and back to pi. You'll see the relationship between those matrices and B. All right, that's enough of that. That's more recreational math, unless it's on the test. And it's actually something that you should probably study. Or what?
Something you said in the range of hard drive storing.
These things?
Yeah.
I don't know, but I know for a fact that for B and C, these are rotation matrices for graphics, computer science and graphics. And by rotation matrices, you should make that connection now with the angles, and yeah. We'll come back to that later. All right, a couple more things before we get to the more algebra part of the matrix. More definitions. Transpose. The transpose of the matrix is really just a way where you can change the rows and the columns. So you make the rows as columns and you make the columns as rows. And so the size of the matrix, it doesn't matter if they're square or not. You'll when you say transpose, you're actually going to switch number of rows and number of columns. So an m by n matrix transpose is going to be an n by m matrix that have gone the other way. And then going and piggybacking along with the transpose, if you have a square matrix and your transpose is equal to the original matrix, then you must have had a symmetric matrix. And symmetric matrix just says that, you know, whatever you have across the diagonal is the same, and so the transpose would be itself again. All right? So I guess we should do just a couple of really simple examples. If your A is equal to 1, 2, 3, 4, 5, 6, 7, 8, then your A transpose is equal to 1, 2, 3, I guess I should be reading it the other way. 1, 3, 5, 7, 2, 4, 6, 8. So that's basically what the transpose is. And if you mess around with Excel, Excel has a transpose paste option too. If you copy a whole bunch of, if you copy a matrix and you want a transpose of that, you can just paste it as a transpose. Free Mat and MATLAB, the transpose command you'll see in your next HBA is a prime.
We haven't had a test, right?
Yeah, no, we haven't. So, if you have a square matrix, whatever you have here, you should have here. Basically, anything across the diagonal. So, a box, and a box, and a moon, and a moon, and a circle, and a circle, triangle, and a triangle, diamond, and a diamond. So the idea is that if you fold this down or you look across the diagonal, that's what a symmetric matrix is. And so if you take the transpose of that, you're going to get the exact same image. In this case, B transpose is equal to B. So B must have been symmetric. So that's what a symmetric matrix is. And you can, instead of finding the transpose, you can just eyeball it, right, and see what's going on across the diagonal. And this is your diagonal. All right. Well, yeah, you have to do the rotation around the diagonal. Okay, so those are more definitions. Now let's get to some matrix algebra. Let's deal with matrices as if they were vectors or as if they were numbers. You know, we kind of, in the beginning of the semester, we kind of used vectors as tools to describe things. And as we use them as tools, we learned a little bit of algebra around vectors. We learned that vectors are commutative, they have an addition and subtraction, and we saw how that was geometrically, and then we also found out that vectors were associative and some stuff with a scalar multiplication. So the same deal with matrices. What we're going to do is we're going to deal with matrices as if they were the base the basis of operation for our manipulating matrices as if we're manipulating numbers. So let's take a look at some basic properties for matrix with matrix algebra. And some of these we kind of already picked up from the first section, but let's reiterate and formalize them. Addition of matrices is commutative. Addition of matrices is associative. And matrices have an additive identity, and that is 0. And because they're commutative, we don't need to worry about 0 plus A. And 0 here is a 0 matrix. Addition also has, matrices also have an identitive property or identitive inverse, and that's throwing a negative sign in front of it. And we define what it means to throw a negative sign in front of it, right? So everything inside of the matrix will just change signs. Scalar multiple of a sum of matrices can be distributed. And two scalars being added with a matrix outside can also be distributed. Scalar multiplication is associative, and this one can be called the multiplicative identity. And when there's a 1 in front of the matrix A, it's understood that that's oh, I'm sorry, that's a scalar. Sorry, let me erase this because that's not the multiplicative identity. The multiplicative identity is multiplying it with an identity matrix, and that's not the identity matrix. This is a scalar one. Okay, so this is some of the basic properties for matrices. I have some sample problems here. I don't know what they are. Let me take a look. Oh, they just want you to do the algebra. There's some linear combination business. All right, linear combination kind of involves those properties. So let's see if we can do some linear combination examples here. Which one do we want? Let's do number 5. It's a 2x2 matrix. So the question is it possible to write B as a linear combination of the other matrices? To kind of show this, what we want to do is write B is equal to constant or scalar times A1, scalar times A2. So if we can write that out, 2503 is equal to a constant, let's say C1, 1, 2, negative 1, 1, plus C2, your A2 matrix, 0, 1, 2, 1. So if you could do this by inspection, that would be great. That will make things a little bit easier. But if you can't, then we can actually break this down and look at it as a system, since we all know how to. Think 2 and 1 would work? I would believe that if there's any chance, because this is a 0, if there's any chance of this happening, C1 has to equal to 2. And then from there, whatever happens, happens. So what did I say C was equal to? 2. Okay. So 2, 1, 2, negative 1, 1 is equal to 3, maybe. So the other thing is that this thing is a 0. We have 2 times negative 1 here. Is that going to work? Uh, 0, 1, 2, 1. So will this work? Okay, so that's your linear combination. Constant times a matrix plus another constant times another matrix, the other matrix. So you got those. You got that to be a linear combination. Okay. Well, let's do number 7. So 3, 1, 1, 0, 1, 0 is equal to C1. 1, 0 minus 1, 0, 1, 0 plus C2. Negative 1, 2, 0, 0, 1, 0 plus C3 times the third one, 1, 1, 1, 0, 0, 0. So if you have more of these things to deal with, this might be a little trickier. I mean, if you're really good at this, you could probably eyeball it and try to figure out what C1, C2, C3 is. To be more systematic about this, what this is really is a what's it called? What's it called? What? What?
I want to combine the word combine and matrix.
Matrix combination. What I meant to say, no. What I meant to say is that if you look at it component by component, just like you would in the vector, right? Yeah, more or less. Yeah, you'll probably have to do it 6 times. So what's it called? What am I creating here? A system of linear equations. So a C1's gone. This is a 2C2. This is a C3. And you'll end up with having 3 unknowns, the C1, C2, C3, and 6 equations. 6 equations and 3 unknowns. And plus C2, let's just say C3. And then 0, 0, C1, no. Oh, C1 plus C2. Oh, they're all zeros, so that's gone. And the last equation's gone. So this one would be 1 is equal to plus C2. So, wait, where's...
Oh my God.
Okay, so we end up having, after eliminating the other 2 equations, we end up with 4 equations and 3 unknowns, and then we can do a row reduction business. So let's practice that. I was just looking at the test and thought maybe we can practice this. So C1 minus C2. Can I change this, just go directly into a matrix with this? All right, so it's going to be an augmented matrix. I have 1, -1, and +1, and then a 3 for the augmented portion for the first equation. Second equation, I have a 0, 2, and a 1, and that's equal to 1. The third equation, I have a -1, a 0, and a 1, and that's equal to 1 again. And then the last equation is a 1, 1, 0, and that's equal to 1. So let's see if we can actually find a solution for this. So we went from a system of linear equations to a matrix, and we're trying to find solutions. It looks like maybe I can wipe out the zeros. So the second equation already has a 0 in the first component. So I'm going to multiply, keep the first and second row. So I'm just going to add the first row to the third row and replace the third row with that. So that's 0, that's -1, 1 and 1 is 2, 3 and 1 is 4. And then I'm going to multiply the first row by -1, add it to the fourth row. By the way, I'm probably going to get, a row of zeros here. Let's see what happens. -1 and 1 is 0. -1 times -1 is +1 and 1 is 2. -1, -3 and 1 is -2. All right? So what's next? Let's see. do a variety of things. What would you do? The third and fourth would probably wipe out. Second and fourth. I'd probably get rid of the twos. I'd probably use a third row. So I'll multiply the third row by 2 and add it to the fourth row. So everything else will remain the same. And if I multiply this by 2, I'm going to get 0. 4 minus 1 is 3. 8 minus 2 is 6. Probably switch these two. Can I just switch it here instead of rewriting everything? So having switched those two, oh boy, 1 minus 1, 1 and 3, and 0, minus 1, 2 and 4. Now I'm going to do this switch. After switching them, I'm going to multiply the new second row by 2, add it to the new third row. That's probably confusing, huh? So 0, this is 0. Multiply this by 2, that's 4, plus 1 is 5. Multiply this by 2, that's 8, plus 1 is 9. Now, I don't know if there's any other easy way to get around this last bit, but okay, well, let's talk about what happens if we were to go all the way through. So if you just do that last bit, is it 3/5, negative 3/5, just to get that 0, right? And then whatever this is, and Hal's saying it doesn't really matter. It's not 0, whatever it is. So, what does this mean? So that the system is not consistent. It's not a linear combination, right? So I think what happened was that when people got this far on one or a couple of the problems, I don't know, sometimes people didn't get this far. But when they did get this far, they didn't know how to conclude it. And there's different scenarios for these things as well. It depends on if you're working with a homogeneous system or a non-homogeneous system. In this case, it's non-homogeneous, and it's actually an augmented matrix. So there's a difference in whether what type of system you're working with. In this case, we get something that's inconsistent. And I guess to be able to do this, you have to think about translating it back into C1, C2, C3 to see if you get to get something out of it. So what's our main point here? C1 minus C2 plus C3 is equal to 3. Negative C2 plus 2C3 is equal to 4. 5C3 is equal to 9, and 0 is equal to a number that's not equal to 0. So the fact that we got what's it called? What's a false statement called? A what? Contradiction. That'll work. Although, fallacy, yeah. 2 L's? The fact that we got something that's not true and the end of this means that there's no solution. And because it's inconsistent, we can't find a C1, C2, C3 so that B is equal to that. So we can conclude that B is not a linear, or cannot be written B cannot be written as a linear combination of A1, A2, and A3. Is there another way to write this? So there's a word span that we learned a while ago. A span is something that you can write as a linear combination of a set of vectors. So we can extend that idea to matrices as well. The span of the set of matrices A1, A2, A3. The span of a set of vectors is a linear combination of those vectors. A span of a matrix is a linear combination of those matrices. And so in this case, we couldn't find constants, scalars, that would make B a linear combination of these vectors or these matrices. And so we can say B is not in their span. Okay. Any questions about linear combinations of matrices? They're just like linear combinations of vectors, except now you have as many slots as you have the matrices. The m by n, you're going to have m times n of these equations that you're going to deal with. Okay. Span.
Everyone's favorite. Yeah, right.
All right. So there's more properties for matrices. And these properties relate with matrix multiplication. Guess I should have labeled them. So the first one is saying that matrix multiplication is associative. The second one, there's some distributive property for matrix multiplication. And the third one is also a distributive property, but notice that the order of the distribution has to stay consistent. And so this is due to the fact that matrix multiplication is not commutative. So if you're going to multiply something from the left side, you have to be consistent in multiplying it from the left side. If you're multiplying something from the right side, again, be consistent and multiply it on the right side when you distribute. The scalar floating around the matrix multiplication is kind of like the vector dot product that scalar can move around. So you can decide to scale a matrix or factor out a scalar from a matrix, and that might be useful in some computations. And then the identity matrix. So the matrix A does not have to be a square matrix for this identity property to work. You can have A as an m by n matrix, and if you multiply it by an appropriate identity size on the left side, it's the same. You're going to get the identity, or it's going to use the same identity property in that it's going to be the identity times a matrix A is going to be the matrix A itself. And that works for the other way as well. So I think this is worth a quick look. If your matrix A is A, B, C, D, E, F, non-square matrix, I would multiply, if I want to multiply this by an identity on the left side, what size identity do I multiply it by? If I wanted to multiply this by a square matrix on the left side, what's that square matrix going to be? A what by what?
1, 0, 0, 1.
Oh, no, it's
A 2 by 2 or a 3 by 3?
2 by 2.
2 by 2, so 1, 0, 0, 1. And if I do this multiplication, I should get the original matrix back. So this is going to be A, B, C, D, E, F. And likewise, if I have A, B, C, D, E, F, and I decide I want to multiply this by an identity matrix on the right side, what size identity matrix do I need to multiply this by? 3 by 3, so 1, 1, 1. And this would also give me, if I do this business with the rows and columns, I should get, again, A, B, C, D, E, F. Okay? And if you're not remembering, this is something that you should be doing in your head as we're doing this, or writing it down even. If you're looking at the matrix, this is a 2 by 3 matrix, and you want to multiply it by a square matrix to the left. This needs to be a 2 by 2 so that these two numbers are the same. And then your result is a 2 by 3 matrix. Okay, so the same goes for over here. If this is a 2 by 3 matrix you're starting off with, what square matrix do you multiply this by? It has to match up with the second number here. This is going to be a 3 by 3. And so your result, again, is going to be a 2 by 3.
Is that only for the...
This is only for E. This is your example for E. Okay. All right, let's see. Oh, look at this. Find conditions for A, B, C, D such that, remember those conditions problems? Let's see if we can squeeze another one here. Let's do number 23. So this is A, and then B is A, B, C, D. Find conditions on these numbers so that we have a matrix that commutes. So what we need to do is we need to consider AB and BA and show that somehow that they're going to be equal to each other. So AB is 1, 1, 0, 1, and B is A, B, C, D, and this is going to be A plus C, B plus D, C, and D. right? And then the backwards A, B, C, D times 1, 1, 0, 1. So the matrix multiplication for this is going to be A plus B, C, C plus D. Now, if they were to equal each other, these components should equal each other across the way, right? So we have A plus C should equal to A. B plus D should equal to A plus B. C should equal to C. And D should equal to C plus D. So what do we have here? What? A system of linear equations. Hey, we know how to deal with systems of linear equations, right? You can eliminate the C is equal to C over here because that's not important, and then you can reason this out. Let's see, not important, and so what does this imply? What's equal to 0? C equals 0? So we have a solution here. We could technically, since we're experts at systems of linear equations and changing it into matrices and solving for them, we could just make a big system here. But I guess this is, we can do this kind of quickly enough. If this also implies that C is equal to 0, right? So A equals A, D is equal to D. So the only other requirement is B plus D equals A plus B, which means what? A is equal to D. And any restrictions on B? B can be anything, right? As long as A is equal to D. So C has to be equal to 0, D has to equal to A, and then B can be anything. So these are your conditions for A, B, C, and D so that this is going to be commutative. Okay, so this would be an example of some matrices where it's commutative, but in general we have to know that matrices do not commute. All right. We have some properties of transpose, but I suppose that's something that we can pick up next time. So I think we can be done.